Okay. Hello. Thank you for choosing my session as your last session today. Yes, hello everyone. I'm gonna talk about a lot of relatively advanced tips regarding rendering that we've learned from daily support to developers in Japan. Actually, UE5 helps you make stunning graphics easily. However, optimizing performance is still a difficult challenge. And Japanese market is mainly maybe console market, so very strict optimizations are always required. So in this presentation, I'm going to share the tips such as how to debug and how to optimize the UE5 graphics features. This presentation was originally made by Yutaro Sawada, a developer relation engineer in Japan. He is a graphics specialist and he helps a lot of developers in Japan like Square Enix, Bandai Namco, Atlus, Sega, etc. So I'm giving this presentation on behalf of him in English. So who I am? I'm Nori Shinoyama, the lead of developer relations. And actually I've been working at Epic Games Japan for more than 8 years maybe. And I'm also giving another presentation tomorrow. Actually, tomorrow's presentation will be more basic and more easy in general compared to this presentation. So this session, I'm going to introduce advanced tips and debug method. But tomorrow's session, I'm going to share with you the problems and the struggles that Japanese developers faced when they started using UE5. So if you feel that today's talk is too difficult, please come to tomorrow's session if you're interested in graphics. Anyway, today's agenda is super simple. Nanite, Lumen, and VSM, and a couple of development tips. That's it. Let's get started. Okay, let's review what Nanite is first. Actually, I'm afraid if you've already heard similar explanations many times though. But anyway, Nanite is also called virtualized geometry. Nanite divides triangle meshes into clusters and build a hierarchical structure in advance. Then, following the hierarchy, Nanite render clusters having optimal details. The left image shows clusters, and the right image shows the polygons. So high-density meshes are rendered by streaming only the necessary data to memory. So Nanite is capable of rendering such as high details meshes. There is another advantage, which is software rasterizer of Nanite. The software rasterizer enables multiple view rendering of Nanite meshes. It means in Lumen and VSM, Virtual Shadow Map, Nanite meshes can be rendered faster compared to non-Nanite normal meshes. Now, Nanite supports various materials like masked materials and world position offset, but like rendering Nanite with masked materials computationally expensive. So if your target frame rate is 60 FPS on console, still opaque material preferred. So in Fortnite, all trees have polygonal shaped leaves and are rendered with opaque materials. But of course, this doesn't mean that the combination of masked and Nanite is completely useless. So if you don't need to really care about FPS like movies, or if your target platform is only like super high-spec PCs, you can use masked materials. And so let's dig into the Nanite cost with various material types. This is a test map with a lot of trees placed by PCG. And that trees came from Electronic Dream demo. Although they use still masked material, they are great examples because it has a system like in which the color of the leaves changes depending on the position of the tree. And it also has like natural swaying with using world position offset. Although the tree's material is a substrate, but you can easily convert it to a normal material just by reconnecting the last node. So you can use the tree and its materials in your test project easily. And here is an example of the material functions that allows the color of the leaves to have variations depending on their position. I hope you can see the difference, but this allows just one material to look like a variety of trees. It's a really, really useful optimization because less material is preferable even for Nanite. Now let's look at the GPU load on these Nanite trees. The original material is masked and uses world position offset, and the total GPU cost is 24 milliseconds. But if WPO is off, it takes about 40 milliseconds, and then if masked is changes to opaque, it takes only 12 milliseconds. So the main processing GPU loads associated with Nanites are as follows: with buffer, shadow depth, and lumen scene. You can see it with using profile GPU easily, but normally, because rasterization is done in parallel, so you cannot see the cost of each material. But there is a command like show mesh draw events. If you use this command, you can see the approximate processing time for each material. And you can see that the software and hardware rasterization are separated because GPU hardware rasterization is slower to handle very small polygons. So Nanite sends such very small polygons to software rasterizer. Actually, you can adjust the threshold between software and hardware rasterizer by this console command. For example, you can reduce software rasterization, and you can completely turn it off and turn on and off async rasterization. But basically, the default settings works efficiently. But it might be useful to adjust these settings if the rasterizer seems to be a bottleneck on your scene. Basic Nanite optimization guidelines are to reduce overdraw and minimize programmable rasterizer cost, such as masked material evaluation. You can check Nanite overview, overdraw from overdraw view of like Nanite visualization. It shows that rasterization of masked materials causes a lot of overdraw. That's why it's still expensive. And yes, regarding world position offset, you can disable world position offset depending on the distance, so that it can reduce GPU cost. And there is a debug view mode, evaluate WPO in Nanite visualizations. So you can easily find a noticeable but still moving world position offset. In the figure, disabled distance is set at 3000, and the green trees in the foreground are swaying, and the red trees in the background are not swaying by these parameters. And Nanite can handle a very large number of meshes, but it also has some limitations. This GIF image shows that Nanite is broken due to placing too many Nanite objects. The maximum number of nodes and the maximum number of clusters you can put in a scene are limited with these C-birds. And you should also remember, like, streaming pool size is also a factor of the Nanite, the maximum of a Nanite object. Just in case you didn't know, Nanite tools have been discontinued in UE 5.3. It was a tool to set up Nanite in bulk, and it's mainly for project migration. But it has been discontinued anymore because it can be replaced by the normal just content browser. So as you can see, the search bar in the content browser can be filtered by property values. For example, filtering with Nanite on or off, or number of triangles is more or less a certain value. And you can also sort them without column view. And you can make multiple assets as Nanite at once, just from the right-click menu. And it's useful way, but you can also save filters by clicking the plus icon to the right of the search window. It's pretty easy to use. So next, let's move on to Lumen. As for Lumen, I would like to point out that the resolution of the Lumen curves, like reflections on this GIF image, visualize the Lumen theme. So you can see the like a change where the Lumen theme becomes rougher as it gets further away, and eventually turns black, and then like becomes black visible again as it gets closer, like this. So Lumen curves of each object, like their resolution dynamically change, and by default up to 1024. And Lumen doesn't render if the resolution is less than card mean resolution, the console variable. And there are some more C words for this dynamically changing resolution of Lumen curves. Like card texture density scale, it can scale value of density according to the size and distance of the Lumen curve OBB. OBB means oriented bounding box. And the other is card max texture density. You can adjust a coefficient of max size according to the OBB size of the card. So if you want to make distant Lumen curves active or visible, you can raise both texture density values. And also, if you want to reduce GPU load, you can lower both values. You can decrease both values. And let me give some guidelines of optimization of Lumen. As a first step, we recommend adjusting scalability setting first. Actually, scalability high is the settings our games actually use for console and for 60 FPS on consoles. And actions on the other side would be trying to reduce the GPU load on the Lumen card. As an example, just merge Lumen cards or adjustment to lower the resolution, of the Lumen cards, and also use Nanite meshes as much as possible, because Nanite meshes can be rendered faster on Lumen and VSM, as I said before. Actually, that's all for Lumen. Just a few topics, because I would like to take long time to explain virtual shadow map next. Why I want to talk about virtual shadow map? Because unfortunately, we've seen many developers in Japan who give up using VSM because the default pool size is 512 megabyte, so the memory consumption and also GPU load are too high for their games. But I think there is room for adjustment in the memory consumption and the GPU load of VSM. So let me introduce some adjustment methods and how they work. There are two parts: VSM shadow map generation and shadow rendering with the shadow maps. Let's see shadow map generation. One of the features of VSM is that it uses virtual texture, as you already know. But this means that a shadow map is decomposed into tiles, and you can set the appropriate size of each tile, so you can get a high-resolution shadow map. The image on the right shows the radial division of the shadow map. Each tile is also called page and is 128 by 128 resolution by default. So to see how tiles work, to see how pages work, it would be better to review light types on UE5 first. UE has different types of light, such as point, spot, rect light, and directional light, and VSM can work differently depending on the type of light. Though from the perspective of VSM, lights can be categorized into two types. The group of point light, spotlight, and rectolight, and the group is called local light, and the only directional light has, the group is called local light, and the only directional light has a few unique behavior. So let's see local light. Spotlight is, yes, I think a good example to see how VSM work. So first, to visualize tiles, pages, change the view mode to virtual page in the virtual shadow map. And also, you can see detailed information on VSM with the command r.shadow.virtual.showstats, like this. And this is the state of spotlight when viewed from a distance. From the start, you can see the number of requested pages, and the current state is only one requested page. So spotlight like this generates only one page. But as you get a little closer, the VSM is subdivided, and the number of pages requested will gradually increase from 1, 3, 4, 5, and so on. And the screen size of each page is various, but all of them have a fixed resolution, like 128 by 128. Next, point light and rectolight. VSM on point light and rectolight work like a cube map. So at least 6 pages are requested, even in the far view. As we get closer each of the 6 sides will be subdivided into more pages, so more pages will be requested. So VSM on local light is subdivided according to the distance of the light. But before moving on directional light, let's see how they work when multiple lights are placed. All visible pages of the lights are requested. And all visible pages of the lights are requested. In other words, the more lights there are, the more pages and the more updates can be requested. And VSM has 2 functions for this problem. One is a cache system, and the other is page management. First is the cache system. The cache system is enabled by default. The idea is that if there are no updates to the view and or scene, I try to cache as much titles, as much pages as possible. Furthermore, to reduce cache updates as much as possible, VSM can separately cache like static objects and dynamic objects. This setting is called static separate, and it's also enabled by default. But you need to understand that it has a side effect of doubling the memory consumption of VSM. But separate cache is used on the city sample. But so I suggest you try cache visualization on city sample. You see a lot of people walking around in the city sample, but only dynamic caches are updated. So let's see the cache visualization. Yes. By switching view mode to cache page in VSM, you can see the cache this visualization mode. And in the cache visualization, like the blue area means the updated dynamic cache like this. Next is page management. I mentioned earlier that the more lights you place, the more VSM shadows map are needed. But the overall number of pages is still limited with the console variable named max physical pages. And the default value is 4096. So shadow maps for all lights are managed in a single pool, texture to the array, and if the cache is separated, this means that you have to have two memory pools. So let's do a simple math to confirm the memory consumption of the VSM. Like physical page pool is the largest resource of virtual shadow map. It is yes, R32 buffer, and the resolution of each page is 128 by 128. And as I said, the maximum number of physical pages, 4096, and then it's doubled if separate static is on. After all, it becomes 512 megabytes in total. Yeah, this is a default setting, so that's why a lot of people say like, oh, BSM is like memory consumption is really, really high. Yeah. So let's dig into how to reduce the memory consumption of the BSM. First is easy, just reduce max physical pages. So if you set up lights that exceeds the number of pages, like but if you set up lights that exceed the number of pages, shadow will be broken. So it's necessary to make sure that the number of requested pages does not exceed the max page count. Then, if memory size if is a priority for your project, you might need to decide to turn off separate static cache. It, of course, cut memory usage in half, but it also means more pages can be updated. So it means maybe GPU cost increase. And let me show you some useful C words to give bias of size of the pages. The C word is resolution LOD bias local. The local at the end of the command means that this C bar works only to local lights. And -1 or less is for finer detail, and 1 or more is for rougher detail, like this. In addition, there is a C bar called resolution LOD bias local moving. Actually, this is not for memory consumption, but this C bar is really useful to reduce GPU cost when a light is moving. This can only be biased at actually when just timing the light is moving. So when the light moves, as you know, when the light moves, whole cache of the light must be invalidated. So all pages of the light need to be updated. It's really costly, so it's really useful. Actually, yeah, of course, it has the same C bar for directional light. So if you if you change your direction, if you change your directional light value, it's really useful. Actually, so this was how the local lights work. Next, let's look at the behavior of directional light. Unlike local lights, the directional light's position doesn't affect. So directional light's VSM is subdivided radially from the viewpoint, like this. So the closer pages to the camera needs to be more detailed. Basically, it works the same way as local light, but directional light has a creep map that changes the tile size of page radially, depending on the distance from the camera. And there is some adjustment method, and there is a bias setting similar to local lights. I think it's easy to remember because the last word of C word local is just changes to directional, like this. The creep map has two settings, first level and last level. So first level defines how detailed the closest page is, and pages with a level greater than last level will not be rendered. And first level has a default value of 6, which covers the level up to 64 centimeter, And last level, its default value is 22, which means like about 40 kilometers. So let's look at the behavior of each here about first level. And this is first level is 6, and first level is 5. You can see the front area more subdivided. And first level is 4. You can see the further like subdivided. Then next level, next last level, and default is 22, covering approximately 40 kilometers, and lowered to 13, like it covers about 82 meters. And last level is 10. This only covers approximately just 10 meters. So to summarize directional light, basically it has the same options of local lights like LOD bias, but directional light has clip map. So there is a couple of keywords to adjust the range of clip map. This is about shadow map generation. So next, let's go to shadow rendering. To achieve high quality detailed shadow, VSM do shadow map ray tracing, SMRT, which is ray tracing on the shadow map. And the shadow rays are distributed based on the source radius or source angle of the light. So as you can see, like a bigger source angle makes softer shadow like this. And the number of samples affects their performance, and it can be adjusted with these keywords, smrt.ray count for local light and direction light. Increasing this value means increases the quality, but also increase the GPU cost. And oh, it's a good timing, but setting this value to 0, and you can get a hard shadow like this image. But because local light can overlap with light, so the GPU cost increases with the number of samples and the number of lights. So, and as the last part of VSM, let's see some physical ways to optimize VSM. First, like from the perspective of optimization, we need to cache as much pages as possible. And to do so, we need to reduce the number of objects that invalidate the cache. Let's see grassland. Grassland is a good example that cannot take advantage of the cache. In that case, you might want to make the grass not affect VSM and use only only cast contact shadow. Contact shadow is calculated in screen space, so it's just a fake function, but it's still very effective in grassland. As the setting contact shadow length can be set from directional light, and you can turn on and off cast contact shadow in static mesh setting. So lastly, if 5.4 in 5.4, you can use a function to dynamically and automatically adjust page LOD according to pool size. It's really, really powerful function. In this example, the page pool size was changed from 4096 to 100, and it made the memory consumption reduce from 512 megabyte to 16 megabyte. But the shadows are rendered nicely, because their page LOD automatically increased, and so of course the shadow won't be broken. So, you think VSM consume too much memory? If you think VSM consume too much memory, so you can try reduce page pool size on UE 5.4 and try adjust keywords I told you. Finally, this is the final section. Let me share a few other tips. Okay, the first tip is shader print. Shader print visualize some important stats. Like this is implemented with a compute shader that converts various resources into stat data. For example, like .nanite.showstats or .shadow.virtual.showstats. We don't have enough time to dig into each stat today, but I want to tell you that they are really helpful to understand what's going on in GPU, especially like when you need to profile and optimize, their like a project. Oh, and also you can adjust their font size, like spacing, with these console commands. And if you want to customize shader print or have your original debug view like shader print, actually you need to write C++ code and compute shader by yourself. But I would also suggest like searching for the shaderprint.usf file. And so you can see how UE5 implements like shader print. And Radiance cache update might be the best simple example to run it. In addition, shader print includes an implementation that you can zoom in on the mouse cursor. It's actually really helpful, useful. It can be activated, and it can be activated from a console command. And you can move the position you see and adjust the size of the zoom target. The next tip is visualize texture, like VIS command. And this command is compatible with like RDG resources and allows you to view resources in real time. Executing this command will display the list of resources, so you can easily find the name of a buffer you want to visualize. And yes, it has several settings available. Let's see some of them. There is a vispool command to find resources to monitor. You can also sort by just entering by name or by size. And with BMP argument, you can also output the specified resource in its original size. In this example, Lumen theme albedo is exported. Pretty useful to debug. And also, render resources view is also helpful to dig into dig into resource-related issue. Yeah, so for example, this is a really easy way to check large resources, etc. Oh, sorry, we still have 12, 15 minutes. Okay, but actually, thank you for listening. But that's it all. But I explained a lot of tips, but like all of them, tips that Japanese developers have found effective. So I hope at least some parts of this presentation will be helpful to you. But honestly, the original author of this presentation, like Yutaro, prepared much more topics for this presentation. And this is a true agenda. And actually, I did only the first and the second section of it. Yes, this presentation still has more than 70 slides. And I think it's, yeah, okay, please look forward to the slides being made public. Yeah, if you want you to give a presentation, yeah, I can continue, but okay. Thank you for listening.